Okay, so this is going to be a shorter lecture, more of a review lecture of the first three lectures. And what I'd like to do is quickly share with you what I think are some of the most important points from the first three lectures. And then at the end, we'll consider a few conceptual questions. So let's start out by recalling what I'd say is probably the most important idea of the first few lectures, and one that we'll be coming back to several times in this course, which is the row echelon form of a matrix. Okay. So what is the row echelon form? Well, we need to satisfy a few conditions. So first of all of the zero rows are at the bottom of the matrix. And the other condition is that the first non-zero entry in each row what is that called, by the way, the first non-zero entry in each row? That's called the pivot, right? So the pivot in each row is strictly to the right. Of the first non-zero entry in the row above. Okay. So we did this before, but let me just draw an example of a matrix in echelon form, just to emphasize a few things. So we have some non-zero number there, and we have zeros down here. And then maybe we have another pivot here, and then maybe we have one here. And I'm just going to put these dots to mean any number. Could be zero, could be non-zero. And maybe we'll have an augmented matrix, so we'll have a dividing line there, and then maybe some other numbers over here. Let's actually put a pivot in this column. Okay, and then we need all zeros here. And so this is going to indicate a non-zero number. And the dots are just any number. Okay, could be zero, could be non-zero. That's an example of a matrix in echelon form. It satisfies both of these. Here, I guess we don't have any all zero rows, but if we did, it would be at the very bottom. Okay, and then we also have the notion of reduced row echelon form. That's right, REF, row echelon form. So what is the reduced row echelon form? So first of all, it's in row echelon form. Plus two additional restrictions. So first of all the pivots have to be 1, or the number 1, and we have only zeros above the pivots. Okay. So here's an example. Let's just do the same matrix, actually. So we have a 1 there. Okay, that's not allowed to be any number anymore. It has to be a 1. The pivots all have to be 1s. Okay, that can be anything. This has to be a 0. These two have to be zeros. And then these can be anything. We'll have this row with all zeros, and then this has to be a 1, and we have to have zeros above it. So there's an example of a matrix in reduced row echelon form. Maybe this is an augmented matrix also. Okay, so where do these come from? Well, a linear system of equations. It corresponds to an augmented matrix. You just sort of write out all the coefficients in the equation along the rows in the matrix in each of the equations, right? Each equation corresponds to one row in the matrix. And then you have equals some number, and that number comes over here. So a linear system corresponds to an augmented matrix. Augmented matrix. And then that augmented matrix can be put in echelon form. Or row echelon form, or reduced row echelon form. So it can be put in row echelon form. How do we put it in row echelon form? Well, we use the elementary row operations. What are the elementary row operations? Let's just review that really quick. There are three of them. 1, 2, 3. The first one is we can multiply a row by any non-zero constant. The second one is we can add or subtract a multiple of a row from any other row. And the third one, we can swap two rows. Don't forget about that third one, by the way. Often you can just, a matrix won't look like it's even close to echelon form, but if you just swap all the rows, so the first non-zero entries are going down and to the right like this, then you can get it pretty close to echelon form. So how do you actually use these? Well, we've done many examples of this, but often what happens is, what would be preventing it from being in echelon form? We'd have a non-zero entry here, and then we'd have something maybe directly below it that's also non-zero. Okay, and so that would be preventing it from. That would be preventing the matrix from being echelon form. Right, so this is not echelon form. Not echelon form. How would we get this into echelon form? Well, we'd take a multiple of the second row and add it to the third row in order to make that 0, in order to get this staircase pattern. Okay, great. So that's a review of row echelon form and reduced row echelon form and how to get there. But I said this is one of the most important ideas of the class. So why is it so important? Well, we can use row echelon form to deduce a lot of things about the solutions to the system of equations, okay, corresponding to the augmented matrix. So let's recall that really quickly. Okay, so first of all, a system could be inconsistent, right? So a system of equations, a linear system of equations, is inconsistent if... Okay, how do we know a system will be inconsistent? How can we tell from the reduced row echelon form, or even from the row echelon form itself? Well, recall what we're looking for is we're looking for a row. So if it has a row that looks like this, we have all zeros, okay, a bunch of zeros. But then, in this very rightmost entry of the augmented matrix, we have something that's not zero. Okay, so this one, let's say that's not zero, non-zero. If we ever get a row that looks like that, then our system of equations is inconsistent. Notice that this one I drew here has a row that looks like that, right? It's this last row here. So this matrix actually corresponds to an inconsistent system. And what does inconsistent mean? It means no solution to the system, right? So, if we look at the row echelon form, we can just immediately see whether or not it's going to be inconsistent. And you might ask, well, wait a second. What if there's no row like this in the row echelon form, but maybe somehow I can do some more elementary row operations to produce a row like that. And it turns out that can't happen, and that's because the pivot positions in row echelon form are unique. Okay, so once you get to row echelon form, you're definitely going to have the pivot positions that you'll always have. Like you will never be able to change those pivot positions. Okay, so you can immediately see from row echelon form when a system is inconsistent. Okay. Yeah, notice we have these same pivot positions over here. Next, okay, that's how we can tell if a system has no solutions. What if we do have solutions? Well, how many possibilities are there? So, okay, so if the system is, what's the opposite of it? Inconsistent, consistent, right? If it has solutions, at least one solution, okay, then, well, what are the possibilities? So how do we know when a matrix in row echelon form has exactly one solution? Okay, let's do that first. So if a system is consistent, then it has exactly one solution if, okay, well, when will it have exactly one solution? It'll have exactly one solution when there are no free variables. Okay, so this is an example actually where there are several free variables. Those are the columns that do not contain a pivot. And remember, free variables we can choose to be any value we want. Okay, so if we have even one free variable, well, we can choose that to be anything we want and we'll get a solution. Okay, so we're going to have certainly more than one solution. We'll have infinitely many solutions. So we're going to have exactly one solution if there are no free variables. There are no free variables. And how do we see that in a matrix? Well, the same thing. So saying there are no free variables, that's the same thing as saying every column has a pivot. Well, except this rightmost one. So every column in this left part, how do we say that? So every column except the rightmost one. The rightmost one. If we were dealing with an augmented matrix, right? Every column has a pivot. What is that going to look like typically? It will look like this, right? So we have our augmented matrix. Every column is going to have a pivot. So I can't put the pivot over here somewhere for the third column. I have to put it right here. These can be any numbers. I have 0, 0, 0. I have this red bar, and these can be any numbers. Okay. All right. So that's what the matrix will look like when we have exactly one solution. Okay. When will we have infinitely many solutions? Okay. So it has exactly one solution if there are no free variables, which means every column on this left part of the matrix has a pivot. It has infinitely many solutions. Well, we already kind of said it. So it has infinitely many solutions if there are free variables. There are free variables. Or, in other words, how do we see the free variables? Well, the free variables are associated with the columns that don't have pivots, right? So there has to be at least one column. There is at least one column. And again, we're not including this rightmost one, so not including the rightmost one. There's at least one column without a pivot. Okay, we're not including the rightmost one because then we could say, oh, well, this column doesn't have a pivot. But no, we need at least one column associated with the variables. So we need at least one column in this part without a pivot. So here's an example. I mean, this actually would not be an example of infinitely many solutions, right? Because this is actually inconsistent. So often first you want to check if it's inconsistent. then if the system is consistent, then we'll have infinitely many solutions if there's at least one column without a pivot. So let's just draw an example of that. There. So we have 0, 0. Let's make this row all zeros just for fun. I definitely need a 0 there, right? If I don't have a 0 there, I'll be inconsistent. But here's a great example of a matrix in row echelon form that has infinitely many solutions. It's associated with a system of equations with infinitely many solutions. Okay, so that's sort of my little review of the first few lectures. These are some of what I think are the most important points. But you know, let's try to put this into practice. So let's take a few more minutes and let's try to answer some questions. Okay. So questions. And I definitely encourage you after I write the question to pause the video and think about it to see if you can come up with the answer on your own. Okay, so first question. Let's do the following question. So, can a linear system? I'm trying to recall the question I asked in lecture 1. That might have seemed a bit difficult at the time, but now it's actually going to be not so difficult. So, can a linear system of 2 equations in 3 variables? 2 equations in 3 variables. So we have 3 unknowns, but only 2 equations. Can such a linear system have exactly one solution? Okay. So try to think about this yourself and then come back and see what I say about it. Okay, so I think we actually answered this problem in the first lecture. The way we thought about it is we have 3 variables, so we're in 3-dimensional space, and the linear equations in that 3-dimensional space in 3 variables represent planes. The solution to each equation on its own is a plane in 3-dimensional space. And so we were thinking, what if we have 2 planes? You know, can they intersect at exactly one point? And we sort of convinced ourselves that that's not possible. So yeah, the answer is no. But now we can see this in a different way, okay? And that's by thinking about the echelon form. Think about the row echelon form of such a matrix. Even though we basically know no information about the equations, it doesn't matter. Okay, what is the row echelon form going to look like? Well, we have 2 rows, and we have 3 columns over here, and then one column here. Okay. What do we need to have exactly one solution? We need no free variables. Every column over here has to have a pivot. Every one of these 3 columns. Okay, so there's column here, column here, column here. I need a pivot in every column. Okay. But I only have 2 rows, right? So I can only have at most 2 pivots, right? Because a pivot is the first non-zero entry in a row. So I have 3 columns. I can have at most 2 pivots, right? So I will have at least 1 free variable in this system. So let me just write that out. So I have 3 columns, but at most 2 pivots, right? At most 2 pivots. I could have 1 pivot even. Which means, you know, assuming the system is consistent in the first place, right? Which we're trying to create exactly one solution. But this means there is at least 1 free variable. Okay. All right. So that's how I'd answer this question using row echelon form. And in fact, do you see how we can generalize this this statement here? So in fact, any linear system. So let's say we have more columns than rows in this part of the matrix, right? So any linear system with more variables than equations. Well, what can we say? It cannot just have one solution. It cannot just have one solution. It must have infinitely many. Or it could have no solutions, right, if it's inconsistent. But it cannot have only one solution. Not possible. Okay, so this is a pretty broad statement, right? But now we can essentially prove that by just thinking about the echelon form. Okay. All right. Let's do another question. So here's a question. I briefly mentioned the idea of a homogeneous system of equations in the previous lecture, so let's talk about that again. So let's give an example. Okay, give an example of a homogeneous. I'll remind you what that is. A homogeneous linear system. With no solutions. What is a homogeneous linear system? It means the right-hand side is all zeros. So let me do 2 rows again. So here we could have had any numbers there, but if it's homogeneous, then the right-hand side has to be all zeros. If you check the previous lecture, I think 2 of the 3 examples we did actually turned out to be homogeneous linear systems. Okay, we want to create a homogeneous linear system with no solutions. Again, pause the video, see if you can come up with one, and then check back. Okay, so this is a bit of a trick question. Turns out it's not possible. So hopefully you weren't thinking about it too long. Why is it not possible? Okay. Well, what would it look like if we have no solutions? Then the row echelon form of the matrix would have to have a row that looks like this. Okay. So it would have to have a pivot in the very last column here. But it's homogeneous, right? So it has zeros in the last column. And crucially, if we do any kind of row operations, we can never change those zeros, right? Because if I add a multiple of this row to that row, this zero is not going to change, right? So it's actually not possible. And so a homogeneous linear system will always have at least one solution. And that's the zero solution. So it always has. I think I might have mentioned this in a previous lecture also, but it always has the zero solution. The zero solution. What is the zero solution? Meaning just x1, x2. I don't know how many variables we have. To like xn is just 0, 0, 0, 0, 0, 0, 0. Okay, so it's not possible. Okay, let's do another problem. So how about what a true or false question? So true or false? Okay, so let's suppose we have a linear system with infinitely many solutions. So if a linear system has infinitely many solutions, then the claim is, then there must be more variables than equations. Okay, so try to think about this one for a bit. Okay. Well, this is a little bit tricky. So you might think, well, wait, we kind of just we did something similar in this first one, right? So if we have more variables than equations, well, then what we showed is what we cannot just have one solution. We could have infinitely many solutions, okay, or we could have no solutions. But this is not asking exactly that. This is sort of the reverse. So we're starting with a linear system of infinitely many solutions. The claim is that the only way you can get that is by having more variables than equations. Okay? So it's saying if we have less variables than equations, or the same number of variables than equations, then we can never have infinitely many solutions. That's what this is saying. Okay? And that's not true, actually. So this one turns out to be false. So I'll circle the false. How can I explain that it's false? Okay, well, what I have to do is I have to find a linear system that has, so I need to find, in order to explain that it's false, I need to find a linear system with infinitely many solutions but with the same number of variables in as equations, or even fewer variables in equations. So with let's say the number of variables is, I guess, right, like this, right, is less than or equal to a number of equations. So can we find an example like that? Where we have fewer variables than equations, let's say, but we still have infinitely many solutions. Okay, well, what do we need for infinitely many solutions? We just need there to be free variables. Okay. Here's one possible example, right? So what if we just, I mean, it's kind of a stupid example, but what if we just take the equation x plus y equals 1, we have two variables. We need to cook up two more equations, okay? Or, I guess one more equation will be enough. But what if I just multiply by 2, right? And 3x plus 3y equals 3. These equations down here are not conveying any new information, right? But technically I have even more equations than variables. But I have infinitely many solutions because this first one alone has infinitely many solutions. It's a line, right, in two-dimensional space. That line represents the solutions. What would the augmented matrix look like? You could alternatively think about you could construct an augmented matrix that satisfies this condition. So it would look like we'd have something here. We'd have a pivot, something there, something there. In this example, it's 1, 1, 1. And then when we put it in echelon form, these two rows are just going to go away. So we're actually just going to get 0, 0, 0, 0, 0, 0. And you see that what we have here is a free variable. That's a free variable. In fact, we could have put as many 0 rows as we want down here. Right? So this is a false statement. If we have infinitely many solutions, it's not true that we had to have more variables than equations. We could have had the same number of variables than equations, or we could have had even fewer variables than equations. We just had a matrix like this, where we have a free variable in there. Okay, so it was a little bit tricky, but let's see. I plan to keep this video around 30 minutes. We're almost there. Let's just do one more. So true or false? This is one we were kind of pondering in the first video. So a linear system can have exactly, let's say, can we find one with exactly 3 solutions? No more, no less. Okay, what do you think? Well, this one's also false. Why is it false though? Why can't we have a linear system with exactly 3 solutions? Again, this seems like a very broad statement, and one, in the first lecture you might have thought, well, oh, this is going to be pretty hard to prove. But we have all the tools to do it, right? So let's just think through this logic. So we know we have no solution if our echelon form has a row like this. If it does not have a row like this, then we have, at least one solution. There's a certain case where we have exactly one solution, and that's if we have no free variables. If we have no columns that do not contain a pivot. These are free variables. These columns are associated with free variables. Okay. So if we have no free variables, we have exactly one solution. What if we have free variables? The second we have a free variable, okay, like this one, what does that mean? Well, it means we can choose the value of the free variable to be anything we'd like, right? And if we can choose it to be anything we'd like, then we have infinitely many solutions, okay? And that's all. Those are the only possibilities if you really think through this logic, right? So either it is consistent or it's not, and if it is consistent, either we have free variables or we don't. If we don't, then we have exactly one solution. If we do, we automatically have infinitely many solutions. Okay, so that one's false. You can either have, a linear system can only have either 0, 1, or infinitely many solutions. So the only 3 possibilities for a linear system of equations. All right. So that's kind of cool. I mean, this echelon form, it really can tell us a lot. I mean, yeah. Again, if you would have considered this statement in the first lecture, it really seems like something that would be tough to prove. For any linear system, right? I'm not saying how many variables or equations we have even, but it's not possible to have exactly 3 solutions, for example, and that's by considering the echelon form. Okay, so that's enough for systems of equations and echelon form for now. In the next lecture, we're going to be talking about vectors, and the goal is to eventually restate systems of equations in vector form. Okay, and we can use some powerful techniques then. Okay, thanks for watching.